Hello, Rob.
Hi, let's check that everything's working. Mhm.
I can see your note screen at the moment, Rob.
Okay, I shared the wrong one. How's that?
Yep, looks good.
Mhm. Actually, I'm going to do this slightly differently. Okay, do you see my slides right now?
Yep, looks good.
Okay, and if I then grab the, sorry, I'm trying to find my Zoom tools. Can you see the laser pointer, or am I doing that wrong?
I th can see Yep, yep,
Okay,
can see it.
we're good.
Are you turning your camera on? It's up to you.
No, I intended to. I just forgot to hit the button.
You're great.
Okay. I guess we'll give everyone a minute to come in.
Can we still hear you? I'm not sure.
Can you hear me?
Yes, yes, we can.
I was just under my breath muttering to myself. Okay, let us begin, and everyone else who wants to trickle in later may. That's the advantage of the online ones is it's less disruptive when that happens. Thank you everyone for coming to this first inaugural McDonald Institute HQP seminar series. I'm Robert Collister. I'm a postdoc at Carleton University. And on this first very special occasion, I'm going to tell you a little bit about the research I did over the last couple of years on ion extraction schemes for rare decay searches. Just got to be sure I'm in the right window. There we go. Um, so this is a relating for neutrino physics experiments where you're searching to learn about the nature of the neutrino from looking at these rare decays. And so there's a lot we don't know about the neutrino that we're hoping that these types of experiments can tell us about. And I'll go through some of what that is. And get into exactly what goes on in neutrinos double beta decay searches, which is where we're trying to get at these unknowns in the neutrino sector. Then I'll tell you about what ion tagging is and the role that it can potentially play in these types of experiments, and then go through what I've been doing specifically at Carleton. So what do we know about neutrinos? We know they're weakly interacting neutral fermions, so they have no electric charge. They aren't involved in the strong force at all. They're just involved in things like radioactive decays. They come in 3 leptonic flavors, depending on the type of lepton they're paired with, whether that's an electron, a muon, or a tau. There is a corresponding electron neutrino or antineutrino, muon antineutrino, and tau antineutrino. We also know they have 3 different mass states, which are not the same as the leptonic flavor states. And they're related by this unitary transformation called the PNMS matrix here, which tells you what linear combination of one states is the projection of the other when they're involved in the decay. We know the mass differences between these mass states from measurements done in neutrino oscillations. The fact that neutrino flavors that are created, say, in the sun, by the time that neutrino has propagated to Earth to interact in a detector, there is some fraction of them that have changed flavor to a muon or a tau neutrino. And we know the mass differences between the mass eigenstates from those measurements. We actually know the mass differences squared. Which causes a problem that I'll get into in a second. So what don't we know about the neutrinos? We don't know the absolute mass scale. Because we only know those mass differences, we don't know where the actual masses are above the value of 0, which they are in the standard model. We also don't know the mass ordering. Because that's a mass difference squared, we don't know whether they're organized in what's called the normal hierarchy here, where the neutrino mass 1 is lower than mass 2, is lower than mass 3, or whether it's the other way around, where they're up like this, where neutrinos 2 and 1 are heavier than mass 3. And this needs to be resolved in order to understand fully about neutrinos. There's also whether they are Dirac or Majorana fermions. Way back in 1937, Ettore Majorana postulated that the neutrino could be its own antiparticle. There's nothing in our understanding of physics that precludes that. It's just as possible that every interaction of a neutrino is actually done by its corresponding antiparticle. And so, there's lots of these unknowns about neutrinos that make it a very interesting sector to look for physics beyond the standard model. So let's get into about double beta decay. What is this? This happens when the energetics of the state involved prevent a single beta particle from being emitted to get to a lower energy ground state. So if you've got an even nuclei, where then the odd nuclei, that would be a single beta down, is actually in a higher energy state. And so this will not happen because it's not energetically favorable. It's just very strictly forbidden, doesn't happen at all, period. In such a case, you have the option for 2 neutrons to simultaneously decay, emitting 2 beta particles, and then jumping 2 atomic numbers down in Z. And so this happens, but it's very, very rare. The half-lives of these types of processes are measured in like 10 to the 24-ish years. Um, yeah, so they're very rare decays, and you need large experiments to be able to search for them. Uh, but what also can happen where instead of the normal process where you've got two electrons coming out and two corresponding electron antineutrinos emitted as well. This has been observed. You can also have this case here where you have a virtual exchange of the neutrino and the antineutrino between the W bosons, and then only two electrons come out. And if this happens, then this is because the neutrino is its own antiparticle, and therefore they're Majorana. If this is the only process that can ever be observed, then they're Dirac fermions. And so what are you looking for? When you have this case here, where some of the energy can be carried away by the neutrinos, if you're measuring what you can detect, the energy of the electrons, then you'll get a continuous spectrum, this broad featured thing here, where all of the energy of the decay, so like from the mass differences between the initial and final state, all of the energy involved in the decay can be collected by the neutrinos. That can be observed by the electrons is the spectrum, and then you don't see the energy carried away by the neutrinos. And so you would have if you could, you would have a corresponding an anti-correlated function there that would add up to be the total Q value of the decay. If there are no neutrinos involved in the process at all, then all of the energy would be carried away by the electrons, in which case you would measure a monoenergetic peak at the Q value of the decay. So because we can collect all the energy of the electrons, you just have this one infinitely sharp spike, which in practice is actually broadened a little bit by the energy resolution of your detector. And so when we're looking for neutrinoless double beta decay, we're trying to measure a small feature at the Q value of the decay in the energy spectrum collected by your detector. So looking at a little bit of what the observable actually is, in this PNMS matrix, you've got a bunch of terms for mixing angles and phases involved in the relation of the mass the mass eigenstates of the neutrinos to the flavor eigenstates. If there is the Majorana nature of the neutrinos, then you also have this Majorana phase that gives rise to something that's called the effective Majorana mass, which is a linear combination of the masses of the neutrinos, the mixing angles between them, and the Majorana phases. And when you measure this guy, and to get at this guy, you can do this by measuring the half-life of the decay. And so by measuring this, you're able to extract the effective Majorana mass and get back all of these interesting things about the nature of neutrinos. If you did see Majorana neutrinos, then that has a number of immediate implications for physics beyond the standard model. It's immediately you have lepton violation, where the double beta decay no longer conserves lepton number because you've got an initial state that has 0 leptons and a final state that has just 2 non-anti, so straight leptons, not anti-leptons. To electrons, you've gone from lepton number 0 to lepton number +2. That is very important because that has implications for things like baryogenesis, why there's more matter than antimatter in the universe. We would get at the mass ordering from the effective Majorana mass, and this is a new source of CP violation in the standard model. And so this is all really interesting things that would be very, very, very cool to see. So where do we look for double beta decay? It's present in a number of isotopes, so they need to be even, and have the energetics favorable. And your things to consider when you're choosing your target isotope is having a larger Q value for the decay, so the higher energy involved in the decay helps you differentiate it from backgrounds. Things like, beta decays from the rocks around you. If you have a higher energy, then you're able to more easily differentiate at that. You want a higher natural abundance of your isotope so that you don't have to have astronomical amounts of it to get the amount of target isotope you need to have a sensitive detector. And there's a greatly varying cost and availability between the isotopes. Xenon itself is pretty expensive, whereas uh, germanium is slightly less so. And so all of these ones are in the plot here are candidates for that, and I'll talk a little bit about the leading what people have done here. So from that plot, these are some of the measurements that have come out as of 2 years ago. And so interesting thing in this column, I think for sure, is these are the observations of sorry, no, these are the limits on the neutrinoless double beta decay half-life set by these experiments. So when you're collecting events in your detector, depending on your target mass and how long you're looking for, you can put a limit on not seeing a double beta decay. If you don't see a double neutrinoless double beta decay, you can put a limit on what that half-life is. And this is what has been done. And the current state of affairs is that we've got limits in all these guys of about the same orders of magnitude at a little below 10 to 25, or actually, we are at 10 to the 25 years now, or 10 to 26 for Camlin's end. So again, these are very, very long half-lives that involve huge detectors going forward to have the amount of isotopic mass you need to not have to count for 100 years to have a chance of seeing anything. I'll talk a little bit now about the leading measurements. Gerda, Core, and Camlin's End. So they involved, a few hundred kilograms of isotope that they're looking for, that of the isotope that they're using to search for double beta decay. And so they all have like exposure times the isotopic mass, and so what they report is an exposure in like kilogram years. And so that's what you'll hear for these types of experiments for how long they've been counting times the mass of their detector. Why is it important for these different isotopes to be looked at? Why can't we just look at what is the single most promising one? It's because back here, and I didn't really mention this here, is that there is a nuclear matrix element involved in translating the half-life to the effective Majorana mass, which involves like the nuclear physics involved in the parent and the daughter nuclei. And these are not very well understood. These still have relatively large error bars on them. And so if one isotope did see a neutrinoless double beta decay, um, that's interesting, but would not be totally convincing because you always wonder, is this some background event that got misidentified? Whereas if you have it in several different isotopes that are different systems being observed with different technologies, that will be much more convincing. And for something as like groundbreaking as this type of physics beyond the standard model, you really do need a many isotopes looking for this at the same time. And so that way you could hedge against unknown systematics and things like that. There's also the unavoidable two neutrino double beta decay background for the different isotopes. I think all of those, they have been observed so far. They've got half-lives in like the 10 to the 22, 23-ish year range. And so as you're looking for something that's several orders of magnitude more likely, you'll have this very large spectrum that at the end you're looking for just a very tiny bump in it. And so you want to have, with all these different detector technologies, being able to look for that thing different ways. I'll just very briefly talk about the upcoming generation of experiments. So the three leading over 10-ton, multi-ton, sorry, they're called the ton scale experiments these days. And so Legend is the leading one where they'll have 476 germanium enriched germanium detectors. Each that'll be 2.6 kilograms of germanium crystal in them. And this will get a sensitivity to the neutrinos double beta decay half-life target of 1.4 times 10 to the 28 years. Cupid, which is looking for it in molybdenum. They've got molybdenum, sorry, this crystal scintillator that's enriched in molybdenum 100, and they'll have a projected sensitivity of just under the 10 to the 28 years. And then Nexo, which is liquid xenon in a time projection chamber that is enriched in xenon 136, at slightly less than 5 tons of it. And they'll have projecting to have a sensitivity of something comparable to legend. And so this is the upcoming generation experiments, and they're all interesting because if you can reach these sensitivities, then when we're talking about the neutrino hierarchy, mass hierarchy problem, if they all reach these sensitivities, they will exclude the inverted ordering of neutrino masses in what's the word? Not competition, in with complementary measurements from the neutrino oscillation experiments. And so that'll be a very exciting thing coming up in the next probably 10 to 15 years as these things come online and start getting their first physics results out. Let's talk a little bit about exposure scaling. So as I said earlier, when you have your massive detector, you're going to count for 10-ish years, tends to be the lifetimes of these things. And how does your sensitivity scale over those 10 years? And so this is from Legend's preconceptual design report, where if you had a truly background-free detector, as in all events you see are only double beta decay events, then your exposure scaling is linear in time. So just you count longer, you get sensitivity corresponding to how long you count, just linear. Follow the solid blue line here. As soon as you have some background in there where you have a potential source of events that could be misattributed to neutrinoless double beta decay, then you start no longer being linear. You're in one of these other lines that fall off more sharply depending on how many counts per full width half maximum per ton per year you're living with. And so if you're down in like you're expecting 1 count per ton year of exposure, then you're already losing like an order of magnitude on your sensitivity after your 10 years of data taking. And that only gets worse as time goes on. So there would be kind of no point to, well, not as much point to say if you're really pushing the envelope, experiment's working really well, can you count for another couple years? With a large enough background, that's just not a good use of time and resources. Which brings me to the point of ion tagging. So what if when you have a decay event detected in your detector, you could go in and identify the daughter of that decay event? So if, for example, you have a xenon 36 atom that double beta decays to barium 136, what if you could go in and detect that you have a barium 136 atom right there where your decay occurred? Then you would know for absolutely certain that that was a double beta decay event and not something that mimics it like something caused by an activated xenon 137, for example. This is called barium tagging or ion tagging, if you're not being specific to barium itself. It's a complete, strict elimination of all backgrounds that are not caused by double beta decay events. You still have the two neutrino beta double beta decay events, but you should be able to differentiate those based on energy. That's the broad spectrum where you're only looking for the bump at the highest end of that, the Q value. It's also a positive symbol of decay. It would involve kind of no, reconstruction efficiencies or any other sources of errors in your detectors. Just is the ion there? Yes, double beta decay. It only requires you to be able to get at the decay daughter and identify it, and that's it. Simple, right? But how do you find a single ion in a multi-ton detector? If you're looking at Nexo and you've got 5 tons of liquid xenon in there, how do you find the one atom in there, or one ion in there. Well, that's what we're working on. I've already told you about that. But there are not just us working on it at Carleton. There's many different groups around the world for different experiments looking for this. So, for example, the next experiment, which is a high pressure xenon gas time projection chamber, they're looking to do it using chemosensors, where they have these molecules where once a barium is bound to it, so they'll have a coated plane where their ions will drift onto it, and when they're bound to one of these chemosensors, then that chemosensor fluoresces, and so you look for spots of light where there were no spots of light following a detected decay event. And that way, when you see light, you know that you had a barium drift to that location. And so they're working on this, and they've made some good progress being able to design these particular molecules and coat them on surfaces. And in solution, they've shown that this works as you would expect it to. And so they're working on doing this in something more like the conditions that will exist inside their gas TPC. As part of Nexo, we have collaborators in the US at Colorado State University who are looking at using a cryogenic probe to bring the probe in, freeze the ion into a little bit of xenon ice on the surface of your probe, bring it out to where you can then do some spectroscopy to identify that there's a barium frozen into that xenon ice lattice. And so they've shown that they're sensitive to single bariums, and they're learning all kinds of interesting wrinkles in this type of technique where they see that over time the fluorescence of that barium in that spot goes down in a process called bleaching, and how you can regenerate that by reannealing the ice, and then the fluorescence comes back. And so they're doing some very interesting things there, and there's a lot of potential there for techniques that could pay off in the near future. Myself, as part of a team of institutions in Canada, we're looking at a scheme to extract the ion, separate it from the xenon. Sorry, I'll use my mouse to show you here. So here's where you have your decay happening inside the TPC. You identify the location. You come in with a probe with a capillary in it to suck out the ion and some liquid xenon, undergo a phase transition as it's transiting through that capillary by heating it, so that you eject the ion and some xenon gas into another chamber where you've got an RF carpet and RF funnel to separate the ion and guide it through a chamber, whereas the neutral xenon gets pumped away. Then when you're in low pressure, you can load that individual ion into a linear Paul trap down here and do some laser spectroscopy to identify that you have barium there. And then finally, you can load that barium into a multiple reflection time of flight spectrometer to measure its mass. So that way you're sure that you really have a barium-136 and it's not some barium from some other source that you have extracted. And so this is the scheme that we're working on. And our Carleton, we're working on the extraction side of it. Our collaborators in McGill are working on the rest of it. And we have collaborators at Triumph working on barium ion sources to be able to then do a full demonstration of the entire technique from in situ individual barium ions. So let's talk about what we have at Carleton. We have the XO100 TPC. There's a picture of it here. So this is the TPC here, where you have the light collection system at the bottom, crossed wire planes. So that when in the electron cloud coming from an ion, when you have a decay happen, the electrons coming off of it will, or I guess whether it's alphas or betas or whatever, the particle coming off of it will ionize some of the xenon. The electrons coming off those ionization trails get drifted down by the electric field applied by these series of field rings to drift the electrons down to the bottom here, where you have a pair of crossed wire planes. And so by measuring which of these wires detect electrons either hitting them or going past them, you can determine the X and Y coordinates of where that decay happened, and then the time between when you have a scintillation pulse from that, when that ionization happens, to when the ions to when the electrons hit the crosswire planes, that time difference, along with knowing your electric field, will tell you the Z coordinate of that decay. And so that's how you reconstruct an event in a TPC, in a time projection chamber, or TPC. Um, and so we want to do that. That'll tell us where to come in with our capillary probe. The cathode on the TPC, where there's a model of it here, has a lot of holes in the top in the top of it, providing access for our capillary probe. So following decay, you can then come in and fish the ion out through there. So for our ion transport and extraction scheme, we don't want to be doing this with xenon 136 decays, because the half-life of the observed 2 neutrino double beta decay is, over 10 to the 20 years. So we're not going to have very many decay events to fish at. So instead, the plan is to use radioactive ions. So in the uranium decay chain, we have radon 222, which alpha decays with a half-life of 3 days. So you can inject a bunch of radon into your TPC chamber, and then as those decays happen over a relatively short rate, a relatively small rate, go after the decay events of those ones. The daughter of that decay is polonium-218, which has a half-life of 3 minutes. Then it alpha decays down to lead-214. And so if you can detect this decay in your TPC, extract the daughter, and then observe this decay somewhere else on the other end of your extraction scheme, then that coincidence will tell you that you've successfully extracted that individual ion. And so the plan is to use these radioactive ions, because then you can control the rates and have it something that is convenient to work with. To detect these decays on the other side of the capillary, in our detection chamber, we have one of these passivated implanted planar silicon detectors, the PIPs. It's a silicon wafer with some implanted electrodes to collect the charges on, and so it's very good at collecting alpha decay energies. And so that's a CAD model of the setup, showing the probe tip, and I've got a better picture of that on the next slide. But this is what it looks like with the TPC in one chamber, and then the pips in another chamber separated by a wall. So there's no chance of individual ions, drifting somewhere and mimic and being a detected decay to ruin your coincidence. This is what the capillary probe looks like. We have a series of we built this displacement device, which has an X and Y displacement stage at the top. So by using stepper motors to step in your X and Y, you then set the pitch and yaw of your probe, and then having a separate motor to do insertion and retraction. It's all part of this WS-40 wobble stick, which you can see right here. There's the handle of it that gets inserted and retracted. The wobble stick has the handle on the outside of the shaft, and it's magnetically coupled to a rod inside, so that as you depress and raise the handle on the outside, you insert and retract the rod on the inside, and so it's vacuum and pressure tight. The capillary is encapsulated in these peak rods here, because the capillary, its outer diameter is like 1.5 millimeters. So this thing is very small and flexible. So if we wanted to get it into a specific location, we need something more rigid to hold it in position. And so we've run it along the center of some peak rods, because peak is happy to play in the xenon. At the bottom here, there's a copper cap on it. This is part of the homing system. So when we're trying to insert and retract the probe through these holes in the cathode, you need to be absolutely certain where your position is. And so we've built a homing system which is mounted to everything rigidly, so that as you touch positions in the homing system, you can map the coordinates of where your stepper motors are, and so that you're not driving your probe tip where it shouldn't go. The flow through the capillary is controlled by manipulating the pressures in the detector chamber. The cryostat operates at 1 bar, 1.5 bars, and so if you want to control the flow up the capillary, you can do that by manipulating how much you're pumping up the xenon from your detector chamber. And by maintaining that pressure differential at the same, then you can control the flow. The whole scheme works because you're keeping laminar flow through this capillary. And laminar flow is characterized by layers of flow that don't intermix, unlike in a turbulent flow where you've got everything kind of roiling together. In laminar flow, they're very straight, even, they don't overlap. And so an ion being carried in the center of that flow isn't going to drift to different, isn't going to be pushed by the flow towards the wall. And so that's why the whole scheme works. So with that capillary and what we think will operate the pressure as, and then with the condition having to maintain laminar flow, we have run some simulations to see if this whole thing will work. So that's what I'm showing you here. This is the probe tip inside the TPC of liquid xenon. And so this fluid outside is liquid xenon. And we're targeting an extraction volume of about 1 centimeter cubed inside the at the tip of the capillary, which is about how close we think we can get the probe tip to a decay event, taking into account, say, the efficiency of the reconstruction of the TPC. You're not going to get it, sub-millimeter accuracy in the position because of the spacing of the wires and the timing resolution of the pulses and things like that. But we think we can get that to a couple millimeters. And so by targeting, a cubic centimeter at the probe tip, where the ion could, in principle, be anywhere there, that tells us if we'll be able to fish out those ions or not. We also need to account for thermal drifts of the ion. If you have an ion just sitting in a bath, it's going to randomly drift around because of thermal motion. Just things are not at absolute zero, things are not all frozen in place. It's going to kind of bounce around off the xenons as they're also bouncing around with finite kinetic energy. We have measurements of about how big this effect is from XO 200. They did some radon polonium coincidence measurements, kind of like what we're trying to do, except they were looking at both the radon decay and the polonium decay happening inside the TPC. So by seeing, okay, you have a decay here, and sometime later I have a decay there, how much has that drifted around and how much has that broadened in the intervening time. And so from that, if you eyeball those plots, you can get an idea of what kind of an upper limit on that thermal drift effect is. Excuse me. Because it's overestimated in their plots because it hasn't been corrected for the finite resolution of their TPC. So again, they can only reconstruct events to a couple millimeters. And so if you look at their plots, the broadness of the features in it, you can kind of get an idea of what that is, including that inefficiency. And from that, we say, okay, as long as we can live with a thermal drift of about 0.2 millimeters per second, then we're good to be able to get the ion out. And so this outer contour here in the plot is where the flow towards the capillary is at that 0.2 millimeters per second. So in principle, if you could wait as long as you wanted, an ion that exists anywhere inside this contour will eventually make it up the capillary because the flow dominates the thermal drift in that volume. If you then look at this animation here, I'll just start when it loops over, which is in 1 second. A little more than 1 second. We just populate the volume with ions, and you can see that the ones near the capillary tip get extracted much more quickly than the ones that start further out. Anything inside this 1 cubic centimeter volume does make it to the capillary tip within 30 seconds, but things outside that would take even longer, in the minute or couple minute range. This wouldn't really be a problem for the barium, but it is for us where we're using radioactive ions because that polonium-218 daughter has a half-life of 3 minutes. And so if you're trying to extract a polonium-218 and it's taking 3 or 5 or 6 minutes, 1 or more half-lives, then you're going to lose a significant fraction of your ions before it even has a chance to make it to the capillary. So that's why you can't just say, okay, anywhere inside this 0.2 millimeter per second volume is golden. We want something that is a faster extraction than that for the testing purposes. The other interesting feature about this is where in the radius of the capillary do the ions end up? Are they towards the center of the capillary, or are many of these ions out towards the wall? And so that's what this histogram down here shows. The red line is the um, the outer radius of, sorry, the radius of the inner diameter of the capillary. So that's where the steel wall of the capillary is. And so you can see well, almost all of the ions from this cubic centimeter volume end up within the inner 3/4 of that volume, of that radius. This is important, and I'll show this more in the next slide, that any kind of little turbulence introduced by the boiling process, because I said we do a phase transition by heating the capillary of the wall, and so you do get a little bit of agitation right at the edges of the wall. That's the ions you're going to lose, is if they're, sorry, I've lost my laser pointer there. That's where you're going to lose ions if they're out here. But fortunately for our case, for our target volume, they're much more towards the center. And so that should be a less of a source of loss in this scheme. So this is simulations we've done of that phase change. So we have flow going up the capillary, laminar, well, conditions promoting laminar flow, but allowing the simulation to introduce turbulence as we're applying heat. So we need about 40 watts to add enough energy to completely complete the phase transition for the flow rate that we're targeting. So this is the density plot showing you how you've gone from the denser liquid to the less dense gas. And so even where you're applying the heat, there is still a little bit of distance after you've left the heating section where you still have evolution of the phase towards gas. The flow is not largely affected by it. The flow lines, the layers in the laminar flow, especially not immediately beside the walls, do still maintain laminar flow very nicely. This is an animation showing particles that have been introduced in the flow at the inlet of the capillary. And so you do see that, right outside, the ones that start immediately beside the walls don't make it very far. They'll touch the wall. And especially when you have a steel capillary, if you have a charged ion coming into contact with that, it's going to grab an electron, and then you no longer have an ion for the rest of the extraction scheme. So that ion would be lost and would be a penalty of efficiency. But then you also see that right at when your boiling starts, when you're starting to add the heat, you do lose another kind of ring of ions. And so like the outer two rings, of which there are, I think, 10 in these groups of particles. And you can see here when they get further out, because your laminar flow has slowest flow at the walls and fastest flow in the middle, you get a separation in those layers here. So that's why it kind of looks like it's turned into a cone going up instead of a plane of ions. But those outer two rings are what get lost. But as I was just talking about on the last slide, that those outer rings are not populated by ions that would be in our target volume. So it looks like this could be almost 100% efficient, which is what you need for ion tagging, because especially when you're looking for ultra rare decays, you don't want to lose the ion and then not be able to tell that was a double beta decay event. So any kind of losses of efficiency, any step along the way, would make this method not practical for rare decay searches. And then the detection, this is what our detector looks like. Here's a picture of it here. We have the pips here on its disc. We have a series of electric field rings in front of it to guide the ion onto the face of the pips. So we learned that we needed this from these simulations showing that when you have your jet of gas coming out of your capillary, as it goes and hits the face of the pips, it's going to the flow curls around across the face of the pips. And so you have this little region of almost static uh, xenon gas in front of it. And so if your ions in that flow, as it curls around, the ion would be carried by that flow and not actually deposit onto the surface of your pips. But with a little bit of field giving it that push, as soon as it gets in there, the electric field pushes it the last little ways, and then it absorbs onto the surface of the pips and sits until it decays. So that's what we can see the animation of here. That once you apply it, so you can see that it kind of goes and slows down a little bit. This is because the direction of the electric field is counter to the flow on the outside. Only once you're in the field rings does the electric field point in the direction to push the ions onto the surface of the pips. And so you can see there that it comes out quick, slows down, makes another field region, and goes in. This is important because this can be exploited in our system to determine that ions are actually coming out of the capillary and you're not just picking up things in the environment. Because if you turn up your electric field large enough, you can totally deflect all these ions away. So it's not a bug, it's a feature. And I'll exploit that later when I talk about some measurements that we've done. So actually, let's talk about that now. So that's how the scheme will work. But that's, all simulations. We need to prove that this is actually possible. Will ions actually survive the trip up the capillary as they're being carried by flowing liquid or gas? And so what we've done as a kind of zeroth order proof of principle measurement is we've done an untargeted ion transfer through the capillary. So instead of having the TPC and liquid xenon and all that, we've just had the capillary inserted into a chamber where we've got argon and the radon coming from a source, radon 222. Argon because it's much, much, much cheaper than xenon. Xenon is prohibitively expensive if you're doing just kind of fast turnaround science, because if you're working with a xenon, you need to constantly be recovering all of your xenon before you open the chamber to change anything. And so as you're iterating designs, you don't want to have to be doing that. So we're doing this in argon instead. This shouldn't affect any conclusions we draw because sorry, I didn't go into this, but when you're talking about the drag force of a flowing liquid on an object inside of it, what's important is the effective radius of that object, whether that's a sphere or a beach ball in the ocean, or a particle inside a flow of liquid xenon, an ion inside a flow of liquid xenon. The dynamics of how these things go, you're looking at the Stokes drag force, and for polonium in all of the noble gases except helium, it's about the same, especially when you're looking at argon, xenon, and neon, just because of the clusters that are made by the charged ion and a little bit of the gas that's very loosely bound around it and that gets dragged along with it. So it's kind of the same between argon and xenon, which is why we think we can do this in the much more readily available argon. So this is what the setup we have. Very, very simple. We have a source chamber here where we've attached the radon source. So it has a valve, so you can let it emit into the chamber until you get a good amount and close the valve, so you're not just blinding your detector by having a too high a rate. The capillary going between the chambers. So this is sealed. The capillary kind of just dangles in free space between them into the detector chamber, where we have it mounted and held in place in front of the detector, the PIPS detector and field rings, which are in the detector chamber. And then we just have a recirculation pump keeping the pressure difference what we want it to be to maintain laminar flow up the capillary. And so this is what we set up. We looked for several hours every day, collecting counts of what's happening in the detector chamber for various values of the electric field, so that we can kind of turn on and off the ion transfer by deflecting the ions away. And also we reverse the deflection, we reverse the direction of the field to be able to actively repel all ions from the field, the field ring region, so that no kind of ambient ones are on there as well. So you can tell that you can fully turn off your detector using that electric field. This is what some data looks like. So this is with 10 volts on the rings. Sorry, I didn't label this very well. This peak here at 6 MeV is the alpha energy of the polonium-218 decay. So these are the ions that have been transferred. This peak here at a little less than 8, 7.6 MeV is polonium-214. So I didn't show it in the decay scheme, but after the polonium-218 decays into lead-214, there's a couple beta decays to get it back up to polonium-214 and another alpha decay down to lead-210. And lead-210 has a half-life of, I think it's 22 years. So that one sticks around for a long time. But once it does decay, then there's another alpha decay for polonium-210, which is at like 5 MeV. So you can't see it on this plot, but some of the background plots we do have a little feature under here, a few fractions, a few counts per hour of a background here from accumulated events over the many-year lifetime of the detector. But on this plot, you also have the radons. The radons are neutral, so they're decaying anywhere in the chamber. But if they're close enough to the surface of the pips, that alpha is going to transfer through the xenon gas and lose some energy. So you get a much broader distribution and no really sharp peak for the radons because you do not have ionic radon, sitting on the surface of the pips where you get the sharper feature with a well-defined energy incidence on the pips because it doesn't have any intervening xenon to attenuate its signal through. So this main peak is what we're interested in. This is what we're looking to change as we manipulate the voltage on the rings. As we turn up the voltage on the rings to 100 volts, we see that, that peak has shrunk quite a bit, whereas the radon it has not. It's about the same. And these values I'm counting up here is just very roughly speaking, take a cut about there and say anything below that will stay as radon. Anything up to about there will be polonium. And so you're comparing, you're kind of scaling your polonium peak by the number of radons you're detecting so that you're not being confounded by, okay, the temperature in the lab this day was a little colder because it's colder outside and you just have more activity in your system, which is why you have a larger peak. So we normalize by the count of radons to kind of to normalize that out, day-to-day variations out like that out. So that's just kind of what the data looks like, and we're counting poloniums. This is what the results of our collection is. So for many different values of the applied voltage. So that 100 volts, the one I showed you, the 10 volts down here, and then where we turn the direction of the field, reverse it by applying a negative voltage, because we wanted to see that you could really turn it off entirely, and sure enough, you can. It's significantly different than this case where you have it. So this would be the case where you're absolutely not transferring any ions because nothing that comes with the capillary will make it there. Whereas up here, even with a fairly strong deflection field, whatever's in the center of the flow, because as I said earlier, with laminar flow, you have slower flow towards the walls, but in the center you have much larger flow. As you turn up your deflection field, the outer layers are the ones that are going to be deflected away, whereas the inner layers will tend to still make it through there, push into the field region where the field is then pointing in the right direction again, and those ones will still make it to the pips. So that's why you have this gradual step down of kind of turning off the ion flow. It's not, a sudden thing as if everything was at one velocity, and once your field is strong enough, they all get deflected away. No, it's a gradual turn off as the layers in the flow are then sufficiently opposed by the electric force to be fully deflected. And so that really does suggest that we understand what's going on here, that these counts we're seeing on the pips are coming from ions that are coming from the capillary and not ones that are decaying from a radon somewhere in the electric field region that then that daughter gets pushed onto the pips. In fact, if you did have that case where, this was only coming from ambient radon decays happening in the chamber and not from polonium ions being carried up the pips, you would see an opposite effect. Because the way the field lines look in this, and I don't have a plot of that at hand, you need a stronger electric field for ions to off the center axis to make it to the pips. For weaker electric fields, they're more influenced by the grounded wall out here that you've got some larger fringing fields poking in that cause the ions to not make it to the pips, to instead have them hit somewhere on the field rings or that. And so you would see the opposite effect if this was just caused by ambient background decays inside the chamber itself. And so we're really convinced that this is working. This is ions traveling up a steel capillary about a meter long from one chamber to the next, which means that what we were seeing in simulations seems to be working, and this is a very promising way to get ions out of the TPC. So in summary, double beta decay is a unique portal to beyond standard model physics in the neutrino sector. It's the only thing that gets at the Majorana nature of neutrinos. It is fully complementary to the neutrino oscillation experiments, where we'll get a handle on the neutrino mass hierarchy. The upcoming experiments should fully cover the inverted ordering of neutrino masses. So, in the next 10 or 15 years, we should very strongly have a second way to exclude that, even if the neutrino oscillation experiments don't do that by themselves. Beyond that, even larger detectors, where if we continue looking for neutrinos double beta decay, could use something like ion tagging to really get their backgrounds down, because as you get a larger detector, you get additional sources of background, more surfaces that radioactives can emanate from. And so this is a very promising way to kind of scale your detector almost indefinitely. And that's the promise of ion tagging, where you could eliminate all non-double beta decay backgrounds. This is the team we've had working on this at Carleton, two faculty, Raz van Gornia and Thomas Kalfas, myself as the postdoc. We've had a couple of master's students come through as well, and undergrads working on honors projects and summer projects and the like. And that's it. Thank you for your attention. And now, because I'm also the convener of this seminar, I'll handle any questions as well. So if you have something to ask, please raise your hand in Zoom. And yeah. I don't see any hands, so if you do have a question, just shout it out. I think we're a small enough group that shouldn't get out of control. Okay, I have another couple minutes, so we can dip into the extra slides if anyone's interested. Sorry. So there's an interesting question of how to choose how big your detector is going to be. So for something like Nexa, why are you targeting 5 tons of liquid xenon? What makes 5 tons the magic number? And so one way to do this is you decide what sensitivity of Majorana mass do you want. So for example, if you had, the neutrino hierarchy problem looking like this, where these limits are set up by the oscillation experiments, and you want to be complementary to that, you'll say, okay, I want my detector to be sensitive to here to be able to totally exclude the entirety of the inverted ordering. And so answer that question. Then you make some assumptions about your models, choose your nuclear matrix elements based off the most recent calculations, and put that into the expression for the half-life and go from there. And so that'll tell you what mass of isotope you need to get. Um, and so if that's how much xenon 136 you have, then you need to consider, okay, the natural abundance of xenon 136 is something like 10% of natural xenon. So you'll need to enrich that so that instead of having a 50-ton detector, you can have a 5-ton detector. But if you then wanted to go for something beyond Nexo, if you then wanted to get into the normal ordering where you again want a 10 times larger detector, what does that look like if you want to go another order of magnitude down on the effective Majorana mass? And if you do the calculation for that, you're looking at a 600-ton natural xenon or 61-ton 90% enriched xenon detector. So for those of you who know what Nexo looks like, you can imagine a Nexo 10 times bigger. And you'd say, what is this? An experiment for giants? That's a big cavity in SNOLAB. And I think that's it for time. I've got 4 o'clock here. So, oh, go ahead, Hussein.
Yeah, thanks for the nice talk. I was just wondering, like, in your simulations, did you ever notice that, like, when you have your liquid xenon that's being transported, it will start heating up from the sides first and then inwards, right? Like,
Yes.
because the capillary walls are warm.
Yes.
And do you see like any sort of effect where it basically acts like an insulation?
No, we don't see that in the simulations. But what we do see is we see kind of a convergence on the flow towards the center. So as
Mm-hmm.
you're heating it from the walls doing the phase change, your layers of flow are faster in the middle than on the outside of the capillary. So as you're kind of pushing material towards the center, because you're less dense where it's starting to do the phase
Mm-hmm.
change, your center path is accelerating. And so you're kind of drawing everything towards it as well. So even
Okay.
if your ion kind of starts, um, in an outer middle layer, they tend to
Mm-hmm.
be focused towards the center on the outlet.
Okay.
So that's the effect we see for what the heating is actually doing at a finer level than might be observed for here. And it's a relatively small effect that you only kind of really
Mm-hmm.
see because this capillary is so long.
Okay. Cool. Thanks.
Okay. All right, thank you everyone for coming. The next HQP seminar is in February. It's the last Wednesday of the month. I can't remember what the date is off the top of my head. If you are not yet on the HQP mailing list for something like this, please drop me a line or contact Zach at the McDonald Institute to get you added to this. And also on the website there's a form to sign up for mailing lists for things like this. Hope to see you in a month.
It's very Robert.
Thanks, Robert.
Wednesday, the February the 26th is the next one.
Great talk. See you all then.
Cheers.
Cheers, everyone.